Today, we'll be discussing one of the most important experiments in nuclear chemistry. An experiment whose results forever changed the nature of warfare and geopolitics. Today, we are going to recreate the experiment in which Hahn, Meitner and Strassmann demonstrated that the atomic nucleus can be split. This is the discovery of nuclear fission. Nuclear fission was researched, identified and explained by Otto Hahn, Fritz Strassmann and Lise Meitner in January 1939. So it was first identified on December 17, 1938 and then explained in January 1939. To understand why the experiment unfolded the way they did, we need to take a closer look at the historical context. The Curies and Rutherford laid the foundation for nuclear chemistry. Curie demonstrated that radioactive substances can be identified and isolated based on their radioactivity, and Rutherford demonstrated not only the existence of the atomic nucleus, but also that reaction can occur at the atomic nucleus. Well, of course not in a chemical sense, but rather the nuclear reactions that we know today. One of the first observed was the alpha-P reaction on nitrogen-14, which produces oxygen-17. Inspired by this, Professor Enrico Fermi essentially threw half the periodic table into his neutron source and systematically investigated these reactions with the idea that irradiating the heaviest element, uranium, might just produce a new element with a proton number of 93. His publication on the alleged discovery of element number 93 was heavily criticized, not only based on today's knowledge, but even back then. Strong criticism came from Ida Noddack, who hinted at nuclear fission in her response article as early as 1934. We have already examined the discussion about element number 93 in a more detailed video, linked here. Hahn, Meitner and Strassmann also undertook the irradiation of uranium with neutrons, and they wanted to investigate transuranic elements a bit more closely. With today's knowledge, we can say that element number 93 to element number 96 were not produced at that time, as the neutron flux was just far too low. At the time, commercially available radium-beryllium neutron sources contained approximately 1 gram of radium-226. That is a significant amount by today's standards, but insufficient to reach element number 96. They discovered at the time when irradiating uranium with neutrons, a uranium isotope with a mass number of 239 was produced, which, according to the initial interpretation of this transformation series, was supposed to form the transuranic elements. Since the actinide series had not been identified at the time and the concept of F-block elements had not yet been formulated, these elements were classified as platinum group elements. However, the chemistry of newly discovered radionuclides only partially matched the expectation for Ika platinum group elements. Ika was just a placeholder for an element that was in the periodic table below a already known element. Such studies were of course reviewed by other scientists. Experiments conducted by Irene Curie and Pavel Savich led to a more in-depth investigation of the matter, including by Hahn, Meitner and Strassmann. Accordingly, the transformation series of successive beta-minus decays was supplemented as follows. In the case of uranium-239 and 2 other uranium isotopes, 2 successive alpha decays occurred, thereby producing 3 new radium isotopes. These each undergo beta-minus decay that produce not only new actinium isotopes but also thorium isotopes. Of course, radium is already a bit closer to the chemistry they discovered, but we haven't quite gotten there yet. And now we come to the paper that made Lise Meitner's nephew jump out of his chair at the barbershop. This paper went into greater detail about how the radium isotopes were isolated and their decay characterized. And instead of continuing to bore you with text, let's just go ahead and do this now. But with a few small changes that make the procedure and the resulting data significantly more reliable. I would like to emphasize here that this is a laboratory experiment for chemistry students in Mainz, and the experimental procedures for the nuclear chemistry lab are still based on instructions handed down personally from Fritz Strassmann. The co-discoverer of nuclear fission established this institute, and the first version of this lab manual was originally intended to train his own staff in nuclear chemistry work. This is why this lab procedure is as detailed as it is. It comes from the discoverer himself. Now regarding the changes. At the time, the uranium was ammonium diuranate dissolved in nitric acid with a natural isotopic ratio. For radiation safety reasons, 70 micrograms of isotopically pure uranium-235 is used today, as this allows us to avoid additional activity from neptunium. Furthermore, irradiation was not performed using a radium-beryllium source with an activity of 1 curie, but rather the Triga research reactor in Mainz. Irradiation took place for 30 minutes at 100 kilowatts in the carousel. After irradiation, the stock solution has a contact dose rate of more than 1 millisievert an hour and is therefore handled by the assistant. The beaker contains 1 milliliter of barium carrier solution with a concentration of 100 milligrams barium per milliliter. 1 milliliter of strontium holdback carrier with a concentration of 10 milligrams per milliliter, and this is all mixed with 1 milliliter of the fission product solution. We know that the separation solution may contain all fission products, including strontium-90, which we want to separate in order to generate better data for the barium radium separation. The entire mixture is then mixed with 30 milliliters of cold hydrochloric acid. The solubility of salts in their corresponding acids decreases within the main groups. Thus, radium chloride is less soluble in hydrochloric acid than barium chloride. Marie Curie also used this to isolate radium, and in this case we apply the same logic 1 period higher to isolate strontium and barium. As we now know, radium is not present in the solution at all. Thus, barium remains as a solid barium chloride as a filter cake in the Hahn's suction frit, while strontium and other fission products that are highly soluble in HCl are found in the suction flask. At the same time, 4 milliliters of deionized water is brought to a boil, and the filter cake is then rinsed again with 1 milliliter of cold concentrated hydrochloric acid. Just to be sure. The hydrochloric acid should remain cold. Next, the barium-containing filter cake is boiled out with steam. This causes the components of the filter cake to dissolve back into the approximately 4 milliliters of boiling distilled water. It's not a big deal if the filter paper slips, but it's better if it doesn't. Out of curiosity, we also wanted to measure the residue since it contains not only inactive strontium and strontium-90, but all the fission products that are highly soluble in HCl. After adding 1 milliliter of strontium solution and 30 milliliters of cold hydrochloric acid, the mixture is filtered again after cooling. The beaker is briefly rinsed with water and its contents are added to the beta-gamma liquid waste. The filter cake is boiled down again exactly the same way. Then 1 milliliter of iron 3 carrier solution, 1 milligram per milliliter, is added. Iron 3 hydroxide is precipitated using carbon dioxide-free ammonia solution while it being hot. Bring that to a brief boil and then filter it again with a membrane filter. The difference is that we continue working with the filtrate and not the residue. However, we are also interested in the residue. This is why the orange-yellow filter cake is retained. The filtrate is collected in a test tube that has been carefully placed inside the suction frit. A glove finger is needed because the suction flask is contaminated on the inside and we want to continue working immediately with this clean test tube. The beaker may be rinsed with a small amount of deionized water, but it's very important that the barium stock solution, now collected, has exactly a volume of 10 milliliters. And this should be adjusted as precisely as possible afterwards. 1 milliliter of this barium stock solution is then mixed with 2 normal sulfuric acid. As we can see, a nice precipitate forms consisting of inactive barium sulfate, which also contains radioactive barium isotopes as fission products. After scraping off the excess and rinsing with diluted sulfuric acid, the dried and then taped filter cake can be measured. Now we come to the truly groundbreaking part. The proof that the element responsible for the activity is not a new isotope of radium, but rather isotopes of barium. At the time, the experiment was also conducted using a radium tracer. In this case, we use radium-224. Now I would like to quickly mention my measurements with the Radiacode. The device used in this video was the Radiacode 103, as newer models were not published yet when I made this video. Simply holding the device to the fresh fission solution yielded some spectrum, which could be anything, but if we measure the used tracer, you can clearly see gamma lines of lead-212, which is a daughter nucleus from radium-224. Additionally, the measurement of the filtrate, which we are about to make, elegantly shows a peak at 537 kiloelectron-volts, which belongs to fission barium, namely the barium-140 isotope. This proves that our separation was successful, and now we only have radium and barium in solution. With my discount code SIMON2026, you can get 5% off your purchase at Radiacode. And now let's find out how we made these filter cakes. So we used radium-224 as a tracer, and radium was also used back then for the fractional crystallization of the chlorides. The chromates are a bit more reliable in this procedure. For this reason, the walls of the test tubes were saturated with a precipitate of inactive barium chromate. The stock solution is mixed with 2 ml of barium carrier solution. It is then diluted with 10 ml of deionized water and acidified with 4 ml of nitric acid. 1 ml of the fission solution is then added to test tube 1. In test tube 2, 2 ml are added. Number 3, 3 ml, number 4, 4, and for number 6 and 8, I think you can figure out how much was added. 1 ml of potassium dichromate solution is then added to each test tube. A spatula tip of potassium cyanate is then added to all of them. In the test tube 1, we wanted a quantitative precipitation of the barium radium chromate and made it alkaline with ammonia solution so that the dichromate turns into chromate and both alkaline earth metals precipitate out immediately. In the other test tube, potassium cyanate is added slowly and carefully and only as needed. And what chemical process is taking place here? First, we have the dichromate-chromate equilibrium, which depends on the pH value. In acidic condition, we have dichromate, and in alkaline conditions, we have the chromate ion. Both barium and radium dichromates are water soluble. The respective chromates, however, are not. Only radium chromate is less water soluble than barium chromate. To put it simply, as soon as minimal amounts of chromate ions are present, radium tends to grab these ions and precipitate out more readily than barium does. And where does this chromate come from bit by bit? From the potassium isocyanate. The isocyanate hydrolyzes, that is, reacts with water according to this reaction equation. You can see how hydroxide ions are released here, which slowly drives the pH towards the alkaline range as part of this equilibrium reaction. Thus, compared to a fixed amount of chromate ions in the solution, the radium chromate precipitates out more strongly. Of course, we have so little radium that not pure radium chromate forms, but rather a mixed crystal of radium and barium. However, we have an excess of barium compared to chromate. Put simply, the slow precipitation ensures that the available radium will definitely capture the available chromate ions for precipitation, while the barium ends up partially empty-handed at the end of this reaction. Since both the inactive barium carrier and the radioactive barium are statistically distributed in the solution, the radioactive barium nevertheless accumulates comparatively in the solution while the radium accumulates in the solid. The suspension is filtered and then dried for alpha measurement. That is, the radium content is determined using a silicon detector. After being sealed off for beta activity measurements, the samples are then measured in the Geiger-Müller counter. If we add radium-224 to our barium fission solution from the start, we observe something interesting. The alpha count rate increases. That is not surprisingly. If we add radium-224 to our barium fission solution from the start and then we just use more of this solution to produce the filter cake, it's clear that we have an increasingly higher alpha count rate. We added roughly 20 kilobecquerels of radium-224 as tracer distributed over a final volume of 24 milliliters. Then we have 0.8 kilobecquerels of radium in test tube 1, 1.6 in test tube 2, 2.5 in test tube 3, 3.3, 5, and the last one contains 6.66 kilobecquerels of radium. We precipitated these quantitatively through the fractionated precipitation procedure. And it only makes sense that then the measurement at the Geiger-Müller counter also shows increased beta activities in the fractionated precipitation samples. And now some math has to come into play. If you look at how much of the barium beta activity in the filter cake accounts for the possible barium activity present in the solution, we can see that it's 100%. Okay, wow, we just brutally precipitated out all of the barium and radium completely using ammonia solution. But if we run this through for our other test tubes and calculate the ratio of total barium activity in the solution to the barium activity in the filter cake, we realize that we have precipitated only 63% 83.6% of the present barium as a chromate. If we calculate the alpha activity of the radium in the solution, we notice that we precipitated 83.2% of the possible 3.3 kilobecquerels. So we have precipitated more alpha activity than beta activity. So our beta emitter behaves chemically different from our radium-224 alpha emitter. And we know from the start that it was radium-224. In the 8 ml test tube, we have just 45.6% of the present beta activity in the filter cake and still 60% of the alpha activity. If we plot the ratio of the different barium enrichment levels per milliliter of fission solution against the volume fraction and then overlay only the barium fraction on top, and if it intersects the origin exactly, we have clearly proven that beta activity involves an element that is chemically similar but distinct from radium. We have beta radioactive barium in our solution. Or to put it in the words of the great scientists, we conclude our radium isotopes have the properties of barium. As chemists, we must actually say that the new substances are not radium but barium, because elements other than radium or barium are out of question. Together with half-lives of the isotopes, we can now re-identify the decay chain initially reported by Hahn-Meitner-Strassmann. Radium-1 is not radium-1 but barium-143, which does indeed decay with a half-life of less than 1 minute, but not into actinium-1 but rather lanthanum-143, which then, with a half-life of less than 30 minutes, decays not into thorium but into cerium-134. Radium-2 is in reality barium-141, which undergoes beta- decay into lanthanum-141, which with approximately that half-life then decays into cerium-141 with a half-life in the hours range. Radium-3 is actually barium-139, which decays with the specified half-life into stable lanthanum-139. And radium-4 is barium-140, which decays with exactly the specified half-life into lanthanum-140, where the half-life was again determined quite accurately. And that further decays into stable cerium-140. It is absolutely impressive how precisely the half-lives could be determined back then, because all of the radionuclides of the respective elements were present in parallel, and one had to calculate all of this from a huge decay curve that was recorded over weeks. They also conducted the experiment countless times in a row back then. The students in the lab of course performed this experiment once. Although the result is more of a rough estimate, the deviation of course can be minimized by the root cause of the deviation, which is the radium-224 tracer itself. It produces radioactive daughter nuclides and thus distorts the measurement. If you perform the analysis not the old-fashioned way with the Geiger-Müller counter, but with a high-purity germanium detector, not via alpha activities, but via the 241 keV radium-224 line, you can circumvent the problem and arrive at a curve shown earlier. This clearly intersects the bisector. Furthermore, we measured the fission product's distribution as it is, directly at the high purity germanium detector. And when I plot the radionuclides sorted by mass against their presence or absence, I get a graph that looks something like this. Does that look familiar? It's a simplified version of the mass-dependent fission yield. We can clearly see that certain masses were produced more readily than others. This insight was not made at the time and could not have been explained since Lise Meitner, together with her nephew, described nuclear fission using the liquid drop model. In this model, the atomic nucleus is viewed as an electrically charged liquid drop. The Bethe-Weizsäcker formula based on this liquid drop model is therefore also very well suited for understanding the energy release during nuclear fission, but this graph cannot be explained. In another practical experiment to identify short-lived fission products, we will take a closer look at that and the theoretical foundation of nuclear fission. With that being said, a big thank you goes out to Yannick Lohmann, who made the filming in the experiment possible as lab supervisor, as well as to the staff of the Trigger Research Reactor in Mainz, and to Professor Dr. Reich, who is responsible for this course. And of course, to all my Patreons for their financial support. With that being said, thank you for your attention and goodbye.